This first example will hopefully show how the arc length formula can be very unwieldy. One typically evaluates the arc length integral exactly only in special situations, and even then, only after some careful algebra. So here we want the arc length for the curve, where x is 3t squared, y equal 4t cubed, with parameter interval from 1 to 4. Of course, here's x of t, here's y of t. And even without sketching the curve, we can go ahead and write an integral for the length. Parameter interval is from 1 to 4, and we integrate the speed. That's x prime of t squared, y prime of t squared dt. X prime is 6t, y prime is 12t squared. Square both under the square root. 36t squared plus 144t to the fourth. There's a common 36 and a common t squared under the square root. Gives me 1 plus 4t squared dt. With that product structure under the square root, go ahead and pull out the 36t squared. It becomes a 6t. And I have left a 1 plus 4t squared. Lucky me, this is well set for a u substitution. So I'll try u equal 1 plus 4t squared. Du is 8t dt. Multiply both sides by 3/4. That gives what I want. Also, when t is equal to 4, that corresponds with u equal 65. T equal 1 corresponds with u equal 5. So I'll convert my t integral into a u integral. Goes from 5 to 65. Substitution was to make the square root simpler. It becomes square root u. And I have left to convert this. 6t dt is 3/4 du. That's using this. Finally, antiderivative will be 3/4. I'll add 1 to the power on u, divide by the new power, plug in the bounds on my integral, and I'll see that my answer, 3/4 divided by 3/2 is 1/2. It's 1/2 65 to the 3/2 minus 1/2 5 to the 3/2. And that's the final answer.